Hi everyone. The topic of my presentation is microscopic and macroscopic properties of HTPB propellant and low temperature dynamical biaxial compression loading. In order to study the microscopic magical properties and macroscopic damage measure of HTPB propellant and low temperature and dynamic biaxial compression loading, the new high-strength testing machine was used to carry out dynamic biaxial compression tests of HTPB propellant in the wide temperature and strength range. Meanwhile, the control test at room temperature was set up, and microscopy was used to observe the macroscopic damage of the loaded suppression. The test results show that temperature and strength significantly affect the magical properties of HTPB propellant in biaxial compression, and the magical properties and biaxial compression loading are more susceptible to temperature than strength. In addition, there is a significant difference between uniaxial and biaxial stress and compression loading. And finally, the effect of temperature and strength on magical properties is closely related to the variation in properties and macroscopic damage measure of HTPB propellants. This paper can depict Richard's understanding of the performance of composite solid propellant and other energetic materials at the macroscopic and macroscopic level, and provide more effective theoretical and technical support for accurate analysis of the grain structure integrity of solid rocket motor and low temperature ignition conditions. The first part is introduction. For the most widely used solid propellant in the SRM grid of missiles around the world, the typical magical properties such as models and strengths of HTPB propellant depend significantly on loading conditions, such as temperature and strength. In addition, in the process of ignition and pressure build-up, the solid propellant grid involves complex stress states, which may be subject to complex mutual axial stresses, such as biaxial compression. Therefore, it is necessary to study the change law of biaxial compression magical properties and related damage measure of HTPB composite solid propellant and diaxial loading at low temperature. However, from the analysis of the previous studies in the lectures, it can be found that insufficient research is done on the magical properties and damage measure of HTPB propellants and dynamical conditions at low temperatures. The second part is experimental facility and methodology. Firstly, HTPB solid propellant used in the present study and was fabricated into cube configuration spacer with a side length of 25 mm for biaxial compression as shown in Figure 1. The structure assembly diagram of the fixture and spacer is shown in Figure 2. The specific test agreement for the dynamical biaxial compression loading test is shown in Table 1. At 24 hours before the equipment, the biaxial compression spacer stored in the glass wall were taken out and placed in the low-temperature test chamber, as shown in Figure 3, for cooling in the order of low temperature in Table 1, and refrigerated for 24 hours at each temperature. After refrigeration, the spacer was quickly taken out and placed in the spacer placement area of the fixture, followed by the dynamic biaxial compression loading test of HTPB propellant at low temperature. With reference to the dynamic biaxial compression test carried out earlier, assemble the biaxial compression fixture with the biaxial compression spacer and the test machine. The diagram of the assembly is shown in Figure 4. Secondly, the macroscopic damage test is mainly based on 1172 micro-CD equipment, and the specific test steps are shown in Figure 5. The miniature specimen size for macroscopic damage test is about 3 mm length, 3 mm width, and 5 mm thickness, and were taken from the typical position of the spacer after biaxial compression loading. The main scanning parameters should be set, which are as follows. The third part is resolution and discussion. Firstly, low temperature reliability analysis was carried out. The result shows that after the specimen is exposed to room temperature for 20 seconds, both the theoretically analyzed and the measured temperature are close to the preset test temperature, which indicates that the specimen temperature change has little effect on the test results. So the test method proposed here compromise reliability of the low temperature test. The results are shown in Table 3. Secondly, considering that the biaxial compression test here studies deformation with a strain of 50%, the Nabisal stress and the Nabisal strain of the used material can't reflect the true magical properties of the material, so the true stress-true strain relationship is used to describe the true magical properties of HTPB propellant. The typical true stress-true strain curve is shown in Figure 8. Certainly, at present, there is no corresponding standard for the determination of magical property parameters of solid propellants and compression loading, especially the determination of magical property parameters and biaxial compression loading. Therefore, this paper mainly refers to Lecture 21 about the determination method of uniaxial compression magical property parameters in magical property tests and uniaxial dynamical compression to define the typical biaxial compression magical property parameters of HTPB composite solid propellant. Based on the defined method for determining the biaxial compression magical property parameters of HTPB propellant, the magical property parameters was extracted from the true stress strain curve upchange and dynamical loading at low temperature, as shown in Figure 8. In this way, we obtain the biaxial compression model, biaxial compression strength, magical properties of unit biaxial compression strain of HTPB propellant at different temperatures and strengths, and their correspondence with the strain range. The results are shown in Figure 10. Furthermore, in order to concretely describe the effects of temperature and strain on the magical properties of HTPB propellant and biaxial compression loading, this section makes analysis using two-factor analysis of Wang. The results are shown in Table 5. First, comparative analysis of uniaxial compression stress and biaxial compression stress was carried out. It can be seen from the analysis in Table 6 that uniaxial and biaxial compression stress radius at different temperature conditions are all less 1, which indicates that the change of compression stress state from uniaxial to biaxial will indeed change the strength of HTPB propellant. In addition, there is a significant difference between uniaxial strength and biaxial strength. The biaxial compression strength at room temperature is about 3 times higher than the uniaxial compression strength. Moreover, it is found that this value almost does not change with the change on temperature. This conclusion can be verified by more uniaxial compression and biaxial compression tests and temperature conditions in subsequent work to obtain the possibility of mutual calculation of uniaxial and biaxial compression stress. Fifth, in order to analyze the magical properties of biaxial compression loading and different temperature and strengths, a macroscopic test can be carried out on the HTPB solid propellant loaded and biaxial compression. Since the 3 design reconstruction mesoscopic correct by squaring with macroscopic equipment is inconvenient for us to analyze the influence of temperature and strain on macroscopic damage intuitively and comprehensively. The tomographic section method is used instead. The results are shown in Figure 11 and 12. Says correlation analysis between macroscopic damage and macroscopic magical properties was carried out. The first part is conclusion. According to the experimental results, the following conclusions can be drawn. Firstly, the biaxial compression magical properties of HTPB propellants exhibit significant temperature and strength depends, and low strength at room temperature. The biaxial compression curve of the propellant exhibits three-segment characters. However, with the decrease of temperature and the increase of strength, the biaxial compression curve characteristic of HTPB propellant gradually changes from three-segment to two-segment character. Secondly, the change of magical properties and biaxial compression displays certain regularity with temperature and strength. The dominant logic of magical property parameters, biaxial compression models, and biaxial compression strength pairs line relationship with the logarithm of strength, and both will increase gradually with the decrease of temperature and the increase of strength. However, no obvious regularity is expressed in the unit biaxial compression strength. In addition, the magical properties and biaxial compression loading are more susceptible to temperature than strength, and biaxial compression strength is more sensitive to temperature and strength changes. Furthermore, the biaxial compression load strength, the HTPB propellant compared to the strength values, and uniaxial compression about 3 times the biaxial compression strength at room temperature, and about 3 times the uniaxial compression stress at low temperature. Thirdly, the effects of temperature and strength on magical properties have a close relation with the macroscopic damage mechanism of HTPB propellants and low strength at room temperature. The macroscopic damage of HTPB propellant will increase with the increase of strength, but further increase of strength will cause changes in macroscopic damage form of propellant and biaxial compression loading. In addition, the macroscopic damage degree of HTPB propellant and dynamical biaxial compression loading at low temperature will gradually deepen with the increase of strength, but the propellant damage form is not changed, only with difference in damage region and degree. Fourth, the future needs further improvement and can gradually only achieve asterisk loading. As a next step, we can use the future design in this paper as a reference to explore biaxial compression test methods with different stress radius, such as 1-2 and 1-4. In addition, the possibility of mutual calculation of uniaxial compression stress can be obtained by carrying out uniaxial compression